time for us to work some more problems. And now this set of problems is focused on two topics. We have our mass and center of mass type problems, and then we have applications of parametric curves. Now, there's not a lot of formulas that apply directly to parametric curves. We do have this important formula, which is length, but we can also do other things which involve things like tangent lines, second derivatives, and we'll get into those as we need it. Of course, once we have length, there's other things we can do. Surface area, volumes, all sorts of fun stuff. So we've got a fun set of problems ahead. We've got lots of stuff to look forward to. As always, do your best to try the problems yourself first. The more that you do by yourself first, the more that you'll learn. The quicker you'll become an expert. I believe in you. All right, let's get going. Determine all t when the parameterized curve 3 tangent squared t plus t squared plus t and 2t plus 1 plus secant squared of t intersects the line x equals 3y. Now you might say, oh, what? What does this curve look like? I can tell you, hopeless. Now you can have a computer plot a bunch of points, but we can't really solve for t and say, oh, this looks like y equals this function. Forget it. Hopeless, hopeless, hopeless. So how do we solve this problem? And we say, well, wait a second, what do we have? Well, what we have is that this first slot is our x. So we're told that x of t is 3 tangent squared t plus t squared plus t. And this slot is our y. So y of t, that's 2t plus 1 plus secant squared t. Now, so far, all I've done is copy down. You're like, well, okay, why did you do that? Well, I just want to point out that this is x, this is y. Here's an x, here's a y. So it's like, oh! So where we see x, we can put in this expression. Where we see y, we can put in that expression. And what do we have? Then we have one formula involving only t. I say, well, that's something we can work with. So we're going to take this expression, 3 tangent squared of t plus t squared plus t. Okay, here's our x, and we're just going to emphasize x equals 3. And plug in this expression, 2t plus 1 plus secant squared of t. And here's our y. Now, hopefully, fingers crossed, we'll be able to make some progress. Well, what can we do? Let's distribute and then move things across. So we'll distribute, and then at the same time we'll move. So we have a 3 tangent squared t, and we also have a 3 secant squared t that's going to move across. So let's go ahead and put this as 3 tangent squared of t minus secant squared of t. We'll see if we can do anything with that. Hopefully we can. There's only that t squared, so okay, plus t squared. There's a t here. There's a 6t over there. Move it across. And then so t subtract 6t minus 5t. And then here, plus 3, move it across. Minus 3 equals 0. Okay, good, good. Now, can we simplify? Well, it's polynomial, but that's not, or is it? Now, tangent squared and secant squared. Do we have anything that relates tangent squared and secant squared together? Yes, we do. There's this really fun formula. And we can find it on our formula sheet, actually. We can just grab it. See how it says here, tangent squared plus 1 equals secant squared? So if you subtract, tangent squared minus secant squared is negative 1. So it's like, aha! Oh, ha-ha. Okay, so this is negative 1. Now, what does that give us? Well, what we can now do is we can distribute. So we replace the tangent squared minus secant squared by negative 1, negative 3 minus 3. We get t squared minus 5t minus 6 equals 0. And now that feels doable. So secretly there was a hidden quadratic in this problem. Now what do we do here? Well, we can do a quadratic formula, but I think this might factor. Two things that would multiply together to give us -6, but if you were to add them, you would get -5. Well, I can think of two numbers that do that. If I take -6 and +1. Let's see if it works. Check the multiplication. T squared, good. Plus t minus 60 is minus 5t, and then minus 6 times 1 is minus 6. So it works. And that gets us to either t equals 6 or t equals -1. So our final answer, all the t where this works, will be the two values, -1 and +6. And there we go. Woohoo! Nice. So it's actually not so bad when you say, oh, wait a second, what can I do? Well, we have x and y. Let's use them as x and y and see what comes out. And yeah, all right, a great start. Let's keep it going. On the given axes, in other words, here, sketch the parameterized curve 2 minus t squared and 2 minus t, where time goes from -1 to 1. Show the proper general shape and label at least 3 points on the curve with their x, y, and t values. All right, well, what do we do? Well, we have to pick some points, so let's go ahead and pick some points. And the way we get the points is we pick some times. And we say, well, not just any times, we have a range here. And so we say, okay, are there some convenient numbers to work with? Because remember, we love ourselves. We want to make the computation easy. And looking at these, well, there's some really convenient numbers floating around. So let's try the numbers -1, 0, and 1. Do you have to pick these? No, you could be exotic. You could say, 1/3 or square root of e over 10. Or, of course, there's infinitely many numbers to pick from. But we're not going to do that because we're going to pick the simple ones. All right. Well, let's plug in. So we'll start with -1. That's probably the hardest one to do here. 2 subtract -1. So that's really 2 plus 1. So that's 3. Subtract -1 squared. So that's subtract 1. So that's going to give us an x value of 2. 2 subtract -1 is really 2 plus 1. So that's 3. 2, 3. Good. Good. How about 0? All right, 2 minus 0 minus 0. And, that's also 2. Okay, yeah, it's okay to have the same x values. Parametric curves, that's totally cool. 2 minus 0 is 2. And, okay, how about t equals 1? 2 minus 1 minus 1, that's 0. And 2 minus 1 is 1. Okay, so let's plot these points. So we have 0, 1, which we'll put there. We have 2, 2, which we'll put there. And we have 2, 3, which we'll put there. Okay, so there's our shape. All right, now, those are some points, but there's lots of ways to connect those. And we want to say, look, we have to have the proper general shape. And so let's go ahead and see if we can't say, well, what does this look like? Well, if we look at our equation a little bit, we say, hey, look at that second slot. So we have our two slots, namely x equals 2 minus t squared, and y equals 2 minus t. Well, we can solve for t in that second thing, so we can put t in terms of y. 2 minus y. And once you can solve for that in one of the slots, you can then substitute in. So what do we really have? We have x is equal to 2 minus 2 minus y minus 2 minus y squared. Okay, so there we go. There's a formula. And now, from here, we actually know what it is because we recognize this. It's a parabola. Now, why? Well, because you see x equals, and then if you were to expand, basically up through y squared terms. We can go ahead and expand. Why not? So this is 2. If you distribute the minus through, minus 2 plus y. And here if you multiply out 4, and then it'll be minus 4y plus y squared. Distribute that minus through again. 2 minus 2 plus y minus 4 plus 4y minus y squared. Okay, and you can get some cancellation. So what do we end up with? Well, we have minus y squared. 4y and y makes plus 5y. And then we have a minus 4. Okay, so this says, aha, this is a parabola. And because it's x in terms of y, it opens sideways. And in particular, because we see a minus y squared, it's opening in this direction. Okay, parabola opening to the left. And we say, all right, well, we're almost done. We say, all right, we know the parabola. And we also, by the way, if you look at the y value, one other thing I want to note is that the y values always change. And so we're not going to have any repetitions. And so we're going to mark some points here. We should have marked t equals negative 1. We're at 2, 3. And here we're at t equals 0. We're at 2, 2. And here we're at t equals 1. And we're at the point 0, 1. And now we're a parabola opening this way. And you see how these two are lined up correctly on top of each other? That means the parabola will go right between there. And you can actually work it out. That's what this tells you. But once you see these 2 points lined up, that says that the center of the parabola has to be somewhere in between. So it's going to come, and then we're going to... Now, you might say, wait, why'd you stop, Steve? Couldn't you have gone further? I mean, couldn't we have kept this going and keep going like that? Or we could have even gone up here a little bit. Why only this piece? Well, because we're asked to sketch the parameterized curve. The parameterized curve has a definite start and stop. We're starting up here at time negative 1, and we're stopping down here at time 1. We're not the whole parabola. The whole parabola, yes, if you have x equals minus y squared plus 5y minus 4, that will keep going. But we're only a piece of it. And so that's why we're definitely going to be stopping at those points, and we don't continue. So there we go. That's the parameterized curve. We've got the proper general shape, and we labeled at least 3 points. We did it! Woohoo! Nice! Find the length of the curve. X equals t squared. Y equals 12t plus 9 to the power of 3/2 over 18. And time goes 2 to 7. So it's a length problem. Now with length problems, there's a couple of varieties that we have. So one of the things you have to do first is say, what variety are we in? Now here we can tell what variety we're in because we see what kind of curve we're dealing with. That's the difference. So the first length problem we talked about was when we had y is a function of x. We don't have that. What we have is parametric curves. We're like, parametric curves. Cool. We have a formula for that. So for parametric, our length is what? Well, it's the integral adding up a to b square root of our x prime of t squared plus our y prime of t squared. All right, well, there's our formula. So we just apply it. And we say, okay, where do we go from? A to B. Well, A to B, 2 to 7. Add up from 2 up to 7. Square root of. Now take the derivatives. And don't rush. Make sure you get these right. Derivative of t squared, 2t. 2t or not 2t? That is the question. No, it's 2t. Plus, okay, derivative of y prime. The 1/18 is a constant, so I'll just write that in front so I don't forget it. Bring the 3/2 power down, so times it by 3/2. And then you're going to have 12t plus 9 to the power of 1/2, right? So the power comes down, subtract 1. Then chain rule, don't forget it. Chain rule, it's a very important rule. Derivative of the inside is 12. Okay, now that's the derivative, and don't forget you need to square that derivative. Sometimes you get so excited, you forget, oh yeah, I need to add a square there. Now, let's see what happens. Notice here we have 3 times 12 gives us 36. And downstairs you have 18 times 2, which gives you 36. So the nice thing, it's almost like somebody planned it. Those all cancel out. We approve that. Okay, so what do we have now? Well, let's go through. We have the integral from 2 to 7 and square root of 2t quantity squared, 4t squared, and then 12t plus 9 to the half squared will be 12t plus 9. Now, we are on the lookout for something that we can integrate because they asked us to find the length, so they anticipate that we can actually integrate. If it had only said set up an equation to find the length, then we could say, aha, we're done. But when they say find it, we actually like, oh, we got to integrate. And when you see something like this, especially when you see like 3 terms, you start saying, well, I bet you this is a square. And so keep in mind, what do squares look like? A plus b squared looks like a squared plus 2ab plus b squared. So we say, well, okay, so if this were a square, well, this would be like the a squared part. So let's call it a 2t quantity squared. And this would be like the b squared. So that would be like a 3 squared. And now the moment of truth. The middle term. Is that the same as 2 times 2t times 3? And if the answer is yes, then life is good. So let's see. 2 times 2 is 4, times 3 is 12. It worked! Yes! Okay. So, happy days. So to be clear, we have the square root of 2t plus 3 quantity squared. Say that we can work with. So this becomes the integral from 2 to 7, 2t plus 3. And now, what's the integral of 2t? T squared. What's the integral of 3? 3t. And we now need to evaluate from 2 to 7. Well, got to plug in. Don't forget to plug in both. Oftentimes we have a 0, not this time. So what happens when we plug in? When we plug in 7. 7 squared is 49. 3 times 7, 21. Subtract. 2 squared, 4. 3 times 2, 6. All right, 49 plus 21, that will make 70. 4 plus 6 will make 10. And 70 subtract 10 gets us to 60. And there we go. We got our answer. Nice. So these aren't too bad. Now, the thing that makes them not too bad is if you just follow the formula, right? We've got the formula, and then just make sure you take your derivatives. Don't forget the square, and don't get creative with square roots. That's a terrible thing. Creativity, we love it, but not when it comes to applying rules of algebra. Rules of algebra are very straightforward, procedural. And so that means you really need to start looking what's inside the square root. Look for the squares. That's one of the big things. Look for squares if possible. There might be some substitutions occasionally, but make sure you respect the square root and follow your algebra. And that's it for this one. Let's go on and do some more. Find a positive value of alpha so that the region where y is bounded from 0 up to 17x to the alpha and x is 0 up to 1 with constant density has x bar is 7/11. Okay. Well, let's think about this for a few minutes. What can we do? Well, what is x bar? It's like we're taking an average. So it's the average location of where the mass is. And so this is a center of mass. Now, you might say, wait, what told me center of mass? And the center of mass type thing is this bar. When you see that bar, definitely center of mass. Okay, so what are we going to do? Well, when we're computing x bar, that's our m sub y over m. It's a moment divided by mass. So we need to do two computations. What's the mass and what's the moment? So let's do a really very simple sketch. So we're going to be a little bit sketchy here, but that's okay. And we have 17x to the alpha. At x equals 0, it's 0, and then it goes up. So I don't know exactly. Let's just pretend like it's this. We don't have to be exact. We just need enough to get some intuition. So we're going from 0 up to 1. And so that's our region. Okay, so here's our region. I'll shade it in. And all right. There we are. Lovely, lovely region. Now, what we want to do is we want to make sure that our center of mass, just as a reminder, we're not computing the y value, we're just computing the x value. So we want to say, x bar, 7/11, it's a little bit past 1. So this is what we want. So in some sense, we want more mass on the right-hand side. All right. Well, with that out of the way, what can we say? Well, let's compute our mass. And, all right, we've got to compute two integrals here. So mass, that's the integral a to b of our density. And then measure, but we're two-dimensional. So since we're two-dimensional, we're going to have our height and our width. Now, notice we have constant density. They didn't tell us what the density is. It actually, in essence, doesn't matter. So it could be constant density, 2, 3, a million. So if it says constant density but doesn't tell you, you say, let's pick it. So we'll pick it to be 1. So constant density, if no other information is given, assume it to be 1. It turns out it won't make a difference. And I'll go ahead and spoil it. If you change the density, you scale the mass. But you also scale the moment. And because you're dividing, the scaling factors cancel. So that's why the density doesn't really matter if it's constant. You can pick the constant, pick it to be nice. Now you might say, why did you go with height width instead of width height? Well, I want to think of doing little vertical strips. And the reason I want that is because I'm thinking of this problem as functions of x for the bounds. So y equals 17 x to the alpha. So since I'm seeing functions of x, I want to think dx. And so, okay, so here we go. We're going to go integral 0 to 1. 1, our height is 17 x to the alpha, and our width is dx. I say, all right, well, that's not so bad. You just add 1 to the exponent and divide. And evaluate from 0 to 1, but of course, when you plug in 0, you get 0. Plug in 1, you get 17, and 1 to anything is 1. Divide by alpha plus 1. All right, good. Now, that's our mass. Wait, hold on a moment, and we got to now compute the moment. And so you might be tempted, set this equals to set. No, that's not what we're doing. It's not that the mass equals 7/11, it's that x bar equals 7/11. Okay, so on to our next round of computation, where we're going to take a moment. So we're specifically looking for m sub y. Now, when you look at m sub y, it's very similar, but it has an extra term, distance. Now, technically, it's not distance, but oftentimes that helps people think about it. It's more appropriately location. So location, density, height, width. So the only thing that really changes is you have this little extra piece added. Okay, so now the question. What is this distance? Well, it's the distance to y. So the distance to y is this distance here, which is given by x. So the only thing that changes is we still have the same bounds. We add a distance in terms of x. Density is still the same. Height is still the same. Dx is still the same. And so really, we say, wow, it's almost the same integral. Almost, but not quite. So what happens is it's now 17x to the alpha plus 1. You add those exponents. So when you actually integrate, you get 17x to the alpha plus 2 over alpha plus 2. Evaluate 0 to 1. And plug in 0, you get 0. Plug in 1, that disappears, and you get 17 over alpha plus 2. Okay, so grand moment of truth. What is x bar? So we're told that 7 over 11 is x bar, but that's equal to our moment, which is 17 divided by alpha plus 2, divided by our mass, which is 17 divided by alpha plus 1. And we're like, cool. Well, if you have a fraction over a fraction, what you can do is you take the fraction downstairs and you flip it over. And so it's 17 over alpha plus 2 times alpha plus 1 over 17. And at this point you might notice, whoa, hey, Steve, that 17 is canceling out. And you are correct. So what does that tell us? It tells us that this 17 actually has no impact on the problem. None. And we could have chosen any number. It's essentially, in some sense, acting in the same way as density did. It turns out it doesn't matter. Now, sometimes it happens, sometimes it doesn't. We shouldn't freak out, but we should say, is that reasonable? And the answer is, well, yeah, because the 17 showed up in both the m and m sub y computations, so it's not surprising that they canceled out. All right, so we're almost there. So what do? Well, we have, so let me go ahead and rewrite this 7 over 11. And now we're going to use a great trick from algebra called cross-multiplying. Get rid of fractions. Fractions are dangerous, and I try to get rid of them whenever I can. And so this leads us to the following. We're going to have 11 times alpha plus 1 is equal to 7 times alpha plus 2. Now, with that in mind, we're almost there. Notice we have one equation for alpha. So 11 alpha plus 11 equals 7 alpha plus 14. We can move the alpha, we can move the 11. 11 subtract 7 gives us 4 alpha. 14 subtract 11 equals 3. 4 alpha equals 3. Divide, we get alpha needs to be 3/4. That's it. We're done. Woohoo! Nice. Now this is, of course, we did x bar. If the question had been about y bar, we would have ended up doing different things. And so keep track, right? It's really important as to what you're doing. And also, of course, if you're thinking x bar, that really is a good reminder. X bar is trying to do the average x. So yeah, we should get x's there. If we've been doing y bar, we should have to add something which corresponded to y. And otherwise, not so bad a problem, right? Yeah, we can do this. We will do this. Find S, the area of the surface generated when the following parametric curve is rotated about the y-axis. So we have 3 plus 2 cosine t and 4 plus 2 sine t, and we're told t is going pi to 2 pi. All right, well, let's see if we can't maybe get a rough picture of what's going on. Okay, so we'll draw ourselves some axes here. Now, if you just sort of use your fingers here and cover up, you'll see, oh, I see 2 cosine t, 2 sine t. What's going on there? What are you drawing? Maybe if you cover up the 2's, you say, oh, cosine t, sine t, that's a circle, the unit circle. So what does the 2 change it? It's the double unit circle? Yeah, so the unit circle is a circle of radius 1. So now it's a circle of radius 2. Well, what does the 3 and the 4 do? Shifts it. Okay, so what's happening is we're going to move. Let's say this is 3 in the x. Here's 4 in the y. And so there's a center here. And we're going to take a circle. Now, what part of the circle? Pay attention. Are we getting all of our circle? Well, normally a circle would be like 0 to 2 pi. We're only getting pi to 2 pi. So that's actually just what? Well, if we think about going around, 0 is on the right-hand side, pi is on the left, and then pi to 2 pi brings us back to the right below. So what's happening here is we're going to go in directions 2 here. So it's the bottom half of the circle. Now, where are we spinning? We're spinning about the y-axis. Okay, so we're spinning here. And so what's going to end up happening is we're going to end up forming some sort of shape here. And you might say, wait a second, I know what this is. This is a bundt cake pan. Like, cool. Finally, math I can get behind. I can use this for cooking, right? Well, maybe, but all right. So anyways, that's the shape. If you don't like the idea of a bundt cake, or like, I've never heard of a bundt cake, think of it as like you take an inner tube and you cut it in half. That's the shape we're forming. Okay, so cool. And so now what's the formula going to do? Well, let's think about it. We say the surface area is integral a to b 2 pi radius length. Okay, that's just the generic formula for surface area. And now we're like, okay, well, now let's really focus in. So when it's talking about 2 pi radius length, the idea is take a little piece of your curve. So here's our little piece. The radius is the distance to where we spin. So here's our radius. So what is the radius? Well, the distance to the y-axis. So if I think of this as being at some location x comma y, how far is the y-axis? And the answer is this is x. And we'll come back and figure out what that means in just a few minutes. Okay, now, what's the length? Well, we need to see what setting we're in. What setting are we in? Parametric. So we say, oh, okay, so for the length, this is going to be our square root of our x prime of t squared plus our y prime of t squared dt. So that's the length. Say, well, wait, now we have all our pieces. All our pieces are in play, so we just need to sort of work these things out. Now, we have a few things. We can talk about a and b. So a and b is for parametric. We'll use our bounds, pi, 2 pi. For x, we use x. So this will become 3 plus 2 cosine t. Cool, cool, cool. And now for the length. Now this is part where we'll have to take a second. Let's work it out here. So we'll do some computations. X prime is minus 2 sine t. Y prime is 2 cosine t. And okay, so the square root of x prime squared plus y prime squared, that's the square root of square of the x prime, 4 sine squared, square of the y prime, 4 cosine squared. And we're like, boy, it'd be nice if that simplified. It would be really nice if that simplified. And then we're like, and it does simplify, right? Because you can pull the 4 out, and the square root of 4 is 2. And then sine squared plus cosine squared is 1. Right? So this is 4 sine squared plus cosine squared. And then this is 1. So it's like, whoa, what does that tell us? Well, that tells us that our length is going to become 2 dt. And now, all of a sudden, like this picture, like, that looks scary. But then we're up to here, and it says, well, we're asked to integrate pi up to 2 pi. And if you multiply these together, 3 plus 2 cosine t times 2, you get 6 plus 4 cosine of t dt. Well, great. We can do that, and we will. All right, what's the integral of 6? That would be, whoops. What did I forget? I was so excited. I forgot the 2 pi. Okay, don't forget. You have to make sure you get all the pieces. I forget that 2 pi with surface area, But because I know I forget it, it's one of those things that I, wait a second, shouldn't that be there? So, learn from your mistakes, right? Even better, learn from other people's mistakes. And then you can save yourself even more heartache. All right, so integral of 6t. Integral of cosine, positive sine. So plus 4 sine t. And we're going to go pi to 2 pi. Now, when you plug in 2 pi, what do we get? So we have 2 pi. 6 times 2 pi makes 12 pi. Sine of 2 pi is 0. Well, that's nice. Subtract. Now plug in pi. 6 times pi is 6 pi. And 4 times sine of pi is also 0. Oh, nice. So 12 pi subtract 6 pi makes 6 pi. So we have 2 pi times 6 pi. Or if you like, that's 12 pi squared. And you're probably like, that's a shame. Because this doesn't make pies, it makes cakes. No, just kidding. Come on. What a beautiful answer. A beautiful answer. All right. Well, yeah, just plug it in. Trust the formula. Make sure you keep track of all your terms. And life is good. It works out in a lovely fashion. Find an equation for the tangent line 2. We have t plus 1 e to the t and t squared minus 3 e to the t at time t equals 3. All right, so when you're after a tangent line, you need 2 pieces of information. So we're going to have to do 2 things. One thing is we need to have a point, and then we need to get a slope. Now, if we think about our point and our slope, we're going to get it from our equation. So you have our x and our y. So our point, well, that'll be at x of 3, y of 3, which becomes 3 plus 1 is 4, so 4e cubed. And then plug in 3 here. 3 squared minus 3 is 6. That's 9 minus 3. And then e cubed. All right, cool. Point there. They might say, is it okay that we have an e cubed? Yeah, e cubed is a number. And it's just like a 4. It's just written in a funny way. So no problem having e cubed as our point. Well, okay, halfway. That didn't take us too long. So what is the second half going to do? Well, we need a slope. Now, how do we do slope? Well, for slope, we say, well, that's really like change in y over change in x. That's what the slope is trying to capture. So, all right, well, that's cool. Cool. So change in y is take the y prime and divide by x prime. So in general, what do we get? Well, we have to take our derivative. So here's a place where I often make mistakes. Sometimes I do the x prime on top and the y prime on the bottom. So I'm always extra cautious. Y prime first. Okay. So 2 things multiplying. Product rule. derivative of the first will be 2t times the second, e to the t, plus the first, t squared minus 3, times the derivative of the second, e to the t. Downstairs, we're going to take the derivative of the first, 1, times the second, e to the t, plus, we can now take the first, t plus 1, times the derivative of the second, e to the t. So sometimes when you have e to the t's, it looks like, it doesn't feel like you're doing things. But that's because the derivative of e to the t is e to the t. Now, before we plug in, let's go ahead and make an observation that everything has an e to the t, so we can factor and cancel it. And so while we don't need to, we might as well say, hey, this is the same as t squared plus 2t minus 3 divide by, and 1 plus t plus 1, t plus 2. All right, now we're ready. So here we go. What do we plug in? T equals 3. So at t equals 3, what happens? Well, we're going to get 9 plus 6 minus 3 over 3 plus 2. 9 plus 6 minus 3 is a number. Let's just go ahead and call it 12. And 3 plus 2 is also a number. Let's go ahead and call it 5. 12 fifths. Oh, 12 fifths. I think that's how it's usually pronounced. All right, good. Now we got our slope. And before we write down the answer, let's talk about some things that could have happened, but they didn't here. What would have happened if we plugged in minus 2? Well, if you plugged in minus 2, you'd see upstairs you'd get a number. You'd get negative 3. Downstairs you'd get 0. If you have non-zero over 0, that means you have a vertical tangent line. So how do you write down the formula for a vertical tangent line? X equals whatever your x coordinate is. So x equals, if you had plugged in negative 2, it would be minus 2 e to the minus 2. Oh, sorry. Minus 1 e to the minus 2. I know how to add minus 2 and 1. What would have happened if you had gone as 0 over 0? Well, more work, right? And so what do? Well, you simplify the expression if you can, and you can also take l'hôpital. Say, l'hôpital. What happens as you get near that slope? And that'll tell you what the behavior should be. All right, but for now, we're happy we got a number. So we have a point, we have a slope, and we write down our formula. So we have, in general, y minus the y value is slope x minus the x value. So for us, that becomes y minus 6e cubed is equal to 12 over 5, or 12 fifths, and x minus 4e cubed. And it didn't tell us to simplify, so we're not going to. We're just going to write it like that. And that is perfectly fine. And so there we go. A lovely answer. A lovely answer. Let x equal t plus 2 sine t, and y equals 3 minus 4 cosine t. Find the value of the second derivative of y with respect to x at time pi over 3. Now, when we found the first derivative, let's remind ourselves of that, because we did that in the last problem, but let's go ahead and remind ourselves just in case we forgot. And we say, well, when we find the first derivative, we say it's change in y over change in x, so it's y prime of t over x prime of t. And you're like, oh, okay, so for like second derivative, is it y double prime over x double prime? No. That would make things too easy. No, it's not because it makes things too easy. It's because that's not what's being captured. We have to step back and say, well, wait, what is the second derivative? What's the second derivative all about? Well, the second derivative is all about saying, how's that first derivative changing for you? Okay, so when we think second derivative, we say, okay, d squared of y over dx squared. It's how is the derivative changing? All right, so that's how we often write it. we say, okay, so what is that really asking? Well, it's really asking what's the change in our dy dx given that we're doing a small change in x, right? How does the derivative change if we change our input? And we say, aha, we know what dy dx is in terms of t. And we know what x is in terms of t. So this is telling us the following. And change, of course, is secret code for take derivatives. This is the derivative of y prime of t over x prime of t divided by the derivative of x of t. Now, if you work this out, and we will, there's sort of two options. You can now just work out a formula and then plug in the appropriate derivatives, or you can say, well, let me plug in what I know now and then take the derivative. I'm not going to say which one is best because the answer is it depends. But let's go ahead and do our chain rule. Sorry, not chain rule, quotient rule. So low d high minus high d low all over low squared. Now, that's just the top. Then you have it divided by x prime of t, right? You have to do it at the bottom. So what's going to happen is there's another 1 over x prime of t. Okay, so that's what we have going on. And, okay, so we can rewrite that as we have x prime, y double prime, minus y prime, x double prime over x prime cubed. Okay, good. Now, there's our formula. There's our x and our y. We just got to start churning. And fingers crossed, we get things which aren't too bad. Well, you can always hope. Let's work through x. So x is t plus 2 sine t, x prime, 1 plus derivative of sine, cosine, x double prime, derivative of cosine, negative sine. Okay, y, 3 minus 4 cosine t. Y prime, well, 3 goes away. Derivative of cosine is negative. And there's already a negative, so that makes a 4, positive 4 sine t. And y double prime, derivative of 4 sine is 4 cosine. Okay. And, all right. Well, let's go ahead. Now, no, we don't need to know x prime. Sorry, we don't need to know x and y. These all involve primes. So let's plug in, right? X prime of pi over 3. Okay, so what would that be? That would be 1 plus 2 cosine of pi over 3. And now we grab our formula sheet and look up. Hopefully cosine of pi over 3 is not bad. Ah, it's not. Cosine of pi over 3 is a half. Oh, thank goodness. So 2 times a half makes 1. So this is 1 plus 1, which makes 2. Good. X double prime of pi over 3. That's minus 2 sine pi over 3. Okay, and then sine pi over 3. Sine pi over 3 is root 3. So 1/2 root 3 times minus 2 makes minus root 3. Okay. Y prime of pi over 3, that's 4 sine pi over 3. Well, it's still root 3 over 2 times 4. And so what we end up with is 2 root 3. And our y double prime of pi over 3, that's 4 cosine pi over 3. And now we said, aha, cosine pi over 3 was a half. We did that earlier. 4 times a half makes 2. Now, why do all of this? Well, because we can now say, aha, at t equals pi over 3. See, we crunch numbers here so that we can say we get x prime of pi over 3, y double prime of pi over 3. Because sometimes what happens is you get really crowded and there's so many terms, you're like, I'm losing track. Wait, I can't keep track of this anymore. Slow down. Slow down. Okay, and we're just going to plug in. So let's read it off. X prime of pi over 3 is 2. So we get 2. Y double prime of pi over 3 is 2. Oh, okay. 2 times 2. Minus y prime of pi over 3 is 2 root 3. X double prime of pi over 3 is minus root 3. Downstairs, x prime of pi over 3 is 2 cubed. And now you're like, wow, that's not so bad. Imagine if we had substituted all these terms in. It's huge. But now it's like, I can do that because you can and you will. All right. Well, we'll do it together. 2 times 2 is 4. Minus minus makes a plus. 2 times root 3 is 2 times 3, also known as 6. And then 2 cubed is 8. So this is the same as 10 over 8. Or if you like, you can divide top and bottom by 2, and you get 5 over 4. And for all those engineers out there, that's 1.2500. High levels of precision. And there we go. All right. Well, good. So the main thing to remember here is if you're dealing with second derivative, it's the change in the first derivative. So it's the derivative of the first derivative divided by x. And if you do it symbolically and you do a little bit of bookkeeping off to the side, it can kind of simplify the computations. And at least, if nothing else, you feel like you write down a lot less. And I think simplifying bookkeeping is a really good way to help get the right answer. Because oftentimes one of the challenges is we get lost in just the jungle of how much we have to write down. So try to simplify your life. Keep things in a nice, logical order. You'll improve your odds of success. And we want you to succeed. Oh yeah. Find mx, the moment about the x-axis of a thin plate bounded by the curve y equals secant x tangent x and the x-axis for 0 less than or equal to x less than or equal to pi over 3 if the density is given by delta equals 7. So it's uniform density. Now you might say, well, okay, can I ignore that? No. You can't ignore it when you're talking about center of mass, but when you're talking about moment, you do need to pay attention. It will come into the computation. The reason being center of mass, you have an upstairs and a downstairs. Essentially, we're just computing the upstairs. All right. Well, let's remind ourselves of our moment. So, in general, when we're looking for mx, this is going to be adding up. So we have an integral. We have a distance, which is really a location. We'll talk about that in a second. And we have our density. And then we have our thing called our measure. But this is a two-dimensional region. So we're going to have our height and our width. All right. Now, we're going to integrate with respect to x. And why do we know we're integrating with respect to x? Well, here, what do we see? We see a secant x tangent x. And we say, when we say a function of x, that makes us think dx. So we're like, okay, I see a function of x, I think dx. So that tells us we're integrating with respect to x, and it helps solve a lot of the pieces really quickly. That gives us our width is dx. Our bounds are given to us, 0 and pi over 3. And our density is given to us. And okay, so that's 7. Now, what is height and distance? So let's talk about these terms. All right, well, let's first do a little bit of a quick sketch here. If you plug in 0 into the function secant times tangent, because tangent of 0 is 0, you get 0. So it starts here, and they're both positive after that, so it goes up. I don't know exactly, but okay, it's going up in some way, up to pi over 3. So here's our region. And now that we have our region, we're saying what's going on? Well, we're thinking of thin vertical strips. Vertical because we're integrating dx. And we say, all right, well, given that we have thin vertical strips, we have to think about what's going on in a random strip. So we say, okay, let's just pick a strip at random. So here's our random typical strip. And our height, well, that's the height of the strip. Now, we have our curve y equals secant x tangent x. So the height would be from the curve to the axis. So our height is secant x tangent x. Now, what's our distance? Well, for distance, we have to say, what does distance really mean? So this is really location with respect to the x-axis, and that's where this x comes into play. Okay, well, that's great. So now what it means is imagine that this rectangle was all we cared about, because essentially that's how it works, right? You just think about little pieces. What's the center? Well, it's the middle point. There's our center. So our distance is from the halfway point down. So here's our distance. Well, okay, so it's the halfway. So it's halfway from secant x tangent x to the axis. So that says this term will be 1/2 secant x tangent x. All right. Well, now we have all our pieces. We've figured out what everything corresponds to. So we just mush it all together, and we'll see what happens to our integral then. Okay, so we have the 7.5 are both constants. And let's go ahead and pull those out for the time being. Integral 0 to pi over 3. And then we have secant x tangent x times secant x tangent x, which I'm going to write very suspiciously as tangent squared x secant squared x dx. And there we go. Once we integrate that, whatever we get, that's the answer. Okay, so how do we integrate it? Well, the good news is that, generally speaking, integrals involving tangents and secants are not too bad, with one exceptional case, which we are not in. We will talk about the exceptional case in a few weeks, and oh boy. But for now, we're like, okay, so what's the clue? Well, what happens is we think of our chain rule, which becomes substitution. And so in substitution, we say, well, look for derivatives. Well, the derivative of secant is secant tangent. Derivative of tangent is secant squared. And then we're like, what? Derivative of tangent is secant squared. Well, we have a secant squared, and then everything else is in terms of tangent. That's nice. So if you can pull a secant squared off on the end and write everything else in terms of tangents, 2 thumbs up to that integral. That is a nice integral. It's the kind of integral we would take home to meet the family. So the substitution becomes tangent du becomes secant squared x dx. And if we make our substitution, well, we still have the 7/2. We update everything. Tangent of 0 is 0. Tangent of pi over 3 is, if in doubt, we look it up. Tangent of pi over 3 is root 3. Okay, so 0 to square root of 3. Then tangent squared x, u squared. And then secant squared x dx, du. And we always update our bounds. Always update our bounds. Why? Because if you update our bounds, you never have to go back. And that's a beautiful thing. So when you have a definite integral, always update your bounds, always looking forward, never looking back. All right, well, we now integrate, and we'd say, well, this is 7/2 integral of u squared, 1/3 u cubed. Evaluate from 0 to root 3. Plug in 0, you get 0. Now we plug in root 3. So this is 7/2 times 1/3. And then root 3 cubed is like root 3 times root 3 times root 3. The reason I'm writing it this way is notice what you have here. You have 1/3, and then you have a root 3 times root 3 on the top. That becomes 1. So we're left with 7/2 times square root of 3. And there we go. That's our answer. A lovely answer. All right. Well, lots of fun things going on. Remember when you're doing m sub x, there's sort of this notion of a half coming into play. So it's half of way between the top and bottom. So you average them. Whereas height is the difference. So when you average, you add and divide by 2. When you difference, you subtract. And I like to just write the formula. I just feel it's so much easier to remember in the generic form and just say, let me fill in all the pieces, and then life becomes great. Well, no, life was always great. We're doing calculus. How couldn't it be wonderful? Consider the curve given parametrically by x of t is this integral 3 to t e to the 3 tau sine 4 tau d tau. These are taus. Think of them as sort of old t's, right? It's the Greek version of t. And then y of t, integral 5 to t, minus e to the 3 tau cosine 4 tau d tau. Now, you might say, can we find these integrals? Not yet, but someday we will. Do we need to find them? Hold on. Let's see what we need to do. Find the length of the curve. Oh. Well, what does the length of curve involve? Well, we know we're parametric because it says with the word parametric, so that's a clue. We know we're length of a curve because it says length of curve. It's like, whoa. They're like flashing a big sign saying, length formula for parametric curves. I'm like, we will listen to your advice, my good friend. All right, so we say, okay, length formula for parametric curve says length is adding up, that's integrating, square root of x prime of t squared plus y prime of t squared dt. So we had a question, do we actually have to integrate these? And the answer is, well, not necessarily, because we don't need x and y, we need x prime and y prime. So let's think about what happens here. What is x prime of t? Well, that's the derivative of the integral 3 to t of e to the 3 tau sine of 4 tau d tau. Now, can we take that derivative? Is there any tool at all available to us? Something that might be very fundamental to the subject of calculus. Fundamental theorem of calculus! Yes! Right? The fundamental theorem of calculus says, hey, if I integrate and then I differentiate, I'm back to where I started. And so, in particular, the derivative of a constant to t of something is just a something expressed as a function of t. So I say, oh, so that says x prime is really e to the 3t sine of 4t. Now, with that in mind, we can just write down y prime without even thinking, right? Because again, taking the derivative of the integral, and you might say, well, wait, that starts at 5. We don't use it to start at 3. We just need it to start at a constant. So this becomes minus e to the 3t cosine 4t. And we've got our derivatives. Okay, so because they wrote our x and y as, find these integrals, Then we say, well, an x prime and y prime are just the things we're trying to find the integrals of. So, okay, well, hopefully that'll help make our computation a little easier. So here we go. We're going from 0 to 2. Right, we read it there. Square root of, and then we have e to the 3t sine of 4t squared plus minus e to the 3t cosine of 4t squared. Well, I don't think this will be hard. I just think we'll have to write down a lot. Let's go ahead and square. We have e. Now when you square e to the 3t, it's e to the 6t. 3t plus 3t. And then sine squared. And then the minus squared goes away. So you have e to the 6t cosine squared of 4t. All right, now, notice you can factor out e to the 6t, and you get sine squared plus cosine squared. And sine squared plus cosine squared is also known as 1. So we end up with e to the 6t. So all those sines and cosines go away. What's the square root of e to the 6t? The answer is e to the 3t. So there's our integral. Well, that's 1/3 e to the 3t. Evaluate 0 to 2. Plug that in. That's 1/3. E to the 3 times 2 is e to the power 6. E to the 0 is also known as 1. So 1/3 e to the 6 minus 1. And ta-da! We're great. We're doing wonderful. And so once you understand, hey, fundamental theorem of calculus, all of a sudden, it's not so bad. It's not bad at all. So good times for us. Find m sub y, the moment about the y-axis of a wire with constant density delta equals 3 that lies along the curve y equals 2/3 x minus 1 to the 3/2 from x equals 1 to 4. All right, so what do we have? Well, let's do a quick sketch. And so we can say, what's this? This is y equals a function of x, which is fine. No worries with that part. A little bit, like, oh, but we were doing so great with parametric. That's okay. We can do great with other things. And x equals 1. You plug in, you get 1 minus 1 is 0. So we start at 0, at 1, and then at 4, well, we're some crazy number, 3 to the 3/2, but we're going up. Okay, okay, let's say we're doing that. All right, so let's say here's our wire. Here's our wire. And so it's a wire, and it has a density. And it's a uniform density along the length of the wire. So cool, that's going to help our computation. And so we say, okay, so we have this wire, constant thickness. I like to think of density as sort of a stand-in for thickness of the wire. And we're looking for the moment. So let's write down what we're looking for. Now, generically speaking, when we're looking for a moment, we are going to add up. So there's an integral, adding things up. And we have our density. Oh, sorry, I forgot about moment. I was thinking mass. Moment, distance first, which is another name for location. Density and measure, which because it's a wire, one dimension, measure means length. So let's talk about our pieces. Let's piece this all together. We can figure out our bounds, right? Our bounds are given, 1 to 4. Cool, 1 to 4. Our density is given. Constant density, boom. Or as I might say, booyah! But we can just say boom. Okay, what about length? Well, what setting are we in? So we're in length. Length has 3 different flavors. We've only talked about 2 so far, but there's 3 flavors. We are in the y equals f of x setting. So our length is going to be the square root of 1 plus f prime of x squared dx. Okay, so let's get into that. So here, this is our f of x. So for us, we have the square root, 1 plus, we have 2/3, and now 3/2 comes down, x minus 1 to the power 1/2, the root of the inside is 1. And that's going to get squared. The 2/3 and 3/2 cancels. X minus 1 to the 1/2 squared becomes x minus 1. And the 1's cancel, so we end up with square root of x dx. Okay, so that's our length. What's our distance? All right, so now let's go back and just think about what's going on. We have our wire. So here's our wire. We're looking for m sub y, which is the moment about the y-axis. And so we say, okay, what is that distance? The distance to the y-axis, that distance is x. So the distance is x. Now we have all our pieces. We distance, density, length. So we put them all together and we have our integral. Okay, so we have integral 1 to 4 of 3x to the what power? Well, we have x times square root of x, so that's x to the 3/2 power. And now we're like, wait, that's it? That's the setup? Yes. So what's left? We just got to carry it out. Oh, the end is near. The end is near. All right, so we're going to add 1 to the power. That makes 5/2 multiplied by 2/5. Evaluate 1 to 4. Okay, so 3 times 2/5, that's 6 over 5. Then we have 4 to the 5/2 minus 1 to the 1/2. Now what is 4 to the 5/2? Well, you can think of it as the square root of 4, which is 2 to the power 5. So that's 32. You can also think of it as 4 to the 5th, which is 1,024, and then the square root of 1,024 is 32. Whichever way works easiest for you. 32 minus 1 makes 31, which unfortunately isn't a very nice number in terms of breaking up. So it's 6 over 5 times 31. But you can multiply 31 times 6, not too hard. That leaves you with 186 divided by 5. And there we go. We found the moment. The moment around the y-axis of our wire is 186/5. All right, we made it. We got through our problems. Woohoo! Yay us. Good job. And I hope you did well. And any parts that you're not doing well, I hope you're learning. And you're saying, aha, I see it now. I'm going to be better. Because that's how you grow, a little bit at a time. Thank you for joining. Thank you for coming and working on the problems with me. Hope you have a great day and good luck in your studies. And perhaps we'll get to meet again. Bye.